For this lecture, we're going to look at rotational spectroscopy. So applying this rigid rotor model to analyze rotational spectra. And for most diatomic molecules or similarly small molecules, the rotational spectrum is in the microwave region of the electromagnetic spectrum, and that corresponds to somewhere in the range of maybe hundreds of megahertz to several gigahertz type frequency. It also can be given in wave numbers, which we've talked about previously. And of course, there's conversion between frequency and wave numbers, and there's also a relationship between energy levels and frequency through the Planck-Einstein equation. It also shows up in the infrared in the combined spectrum, combined rotational vibrational spectrum, in which a vibrational transition is accompanied with a transition in the rotational spectrum. So you start with a system in some initial, so you can start with the system in, say, in the case of microwave, we go from states of one angular momentum L to a different angular momentum quantum number L prime. Actually, we end up using J, as we see momentarily. And in the infrared, we go from V equals 0 to V equals 1, and because you start with almost all molecules, at least at room temperature, most of the molecules, particularly for small molecules at room temperature, most of them are going to be in the vibrational ground state, and so they can absorb an infrared photon going from the V equals 0 state to the V equals 1 state, and at the same time going from some L or J state to some L prime or J prime, some new state. And so those are, that's a little bit about the process. I'll talk about the selection rules, exactly what there's some restrictions on the values of L prime and J prime, or L prime or J prime, that have to do with, that are imposed in rotational spectroscopy because of some physics that we won't have a chance to go into in detail, at least at this point in the semester. However, we can use those selection rules to come up with a scheme for analyzing spectra. And one of the important, there are a few, so one of the important results is that the rotational spectrum, at least for diatomics, gives you information about bond length. And so that can be useful. And it gives you some additional information with fancier analysis and with more data. But that's kind of the starting point, is that rotational spectrum can give you information about bond length and about the masses of the atoms in the molecule. And so this is it turns out that this is a real victory of quantum mechanics, was this ability to explain the structure in the infrared spectrum and in the microwave spectrum of small molecules, and to use that information to give you structural information about the molecule. This is a victory for the quantum theory, and it led to things like the microwave spectroscopy led to things like the ammonia maser, and ultimately, of course, to things like the laser. So first of all, let's talk about some conventions. Or really one key convention, which is if we're talking about rotational spectroscopy, the quantum number is J. So we go from L. L is sort of a generic angular momentum quantum number, this sort of script L. And when we're talking about J, we're talking specifically about rotation of molecules. It could be diatomic, could be larger molecules. It's not too difficult to extend the, we're going to talk primarily about the diatomic treatment to keep things simple, but it's fairly straightforward to extend this to larger molecules. And so then the expression for the energy levels of the rotational energy levels is that E sub j, so energy of the jth level, is h bar squared over 2I j times j plus 1. And this is essentially the same energy level expression that we got from the rigid rotor, where we've replaced L, the sort of script or cursive L, with capital J. And our J quantum number, again, can be in this range, J equals 0, 1, 2, 3. And the other thing that we're not going to explicitly include the M quantum number, but it's there. It's affecting the number of energy levels, and so we get GJ is 2J plus 1. And this is just, and GJ, that's the degeneracy of jth level. And here we've defined degeneracy as the number of states at a given energy level. Okay, so let's work through this a little bit. For j equals 0, that corresponds to L equals 0, and the possible values for the M sub L quantum number are just 0. Whereas if we look at j equals 1, which corresponds to L equals 1, then the possible values of ML are -1, 0, and 1. But ML doesn't affect the energy, and it just indicates sort of the direction of rotation in an approximate way, because we can't, there is no single well-defined plane of rotation for the quantum mechanical rigid rotor. It's kind of a sort of like an aspect of an uncertainty type principle. We just can't know it. But yeah, so then there are 3 states at that energy. So Gj equals 3. And for j equals 2, we get 5 possible values of ML. And again, that corresponds to this, this expression for the degeneracy G sub j. Okay, and another thing, another convention that we introduce, yeah, so one is switching from L to J. The other convention is we define a rotation constant which which is given by h bar squared over 2I. So then our energy expression is B times j plus 1. And one of the reasons why we introduce this rotation constant is this is something that you'll be able to fairly directly observe in the spectrum as being related to the spacing between spectral lines, as we'll see momentarily. The units of B, so looking at this, the units of B would be actually, because the energy levels of the system would be in something like joules, it can be joules. But since we're also talking about spectroscopy, we can be talking about, so we can be talking about the energy of individual photons, and a photon of a given energy also has a well-defined frequency. So it could be in hertz. And so that would be that energy of our photon is h nu, where nu is the frequency. And so it's related to the energy in joules by a factor of h. And B can also be given in wave numbers. Which are sometimes given in units of nu tilde. There's sometimes the symbol used for wave numbers. And it's also, but more typically, it's inverse centimeters. So it corresponds to the number of wavelengths in a given centimeter. And we talked about converting between frequency and wave number before, right? In that if we want wave numbers or reciprocal centimeters, and if we have our frequency in hertz, which of course is inverse seconds, we can convert back and forth using this expression. There's another way too to get a conversion. If you have the energy in joules and you want to go directly to wave numbers, we can use the unit conversion that a photon of one wave number has an energy of 1.986 times 10 to the minus 23 joules. So you can go from joules to frequency, and then frequency to in hertz to frequency in wave numbers, or you can sort of handle it in one conversion. All right. Anyway, so wave numbers is a unit that that shows up in infrared spectrum, so in the rho vibrational spectrum, if you're given that spectrum in units of wave numbers, what the peak positions are in wave numbers, then you can get by examining that spectrum, the spacing between some of the lines is going to be related to this B factor, which you'll be given, which would be in wave numbers, and then you would want to convert to joules in order to get information about the bond lengths, as we'll see. Okay, but before we go into analyzing the spectrum, let's talk a little bit about the nature of the spectrum. So, or no, let's go right into selection rules. Sorry. So for typical molecule, for room temperature, for a typical diatomic, there'll be several J levels are occupied, are partially occupied. So whereas and I don't want to spend too much time going into the statistical mechanics of it and the the Boltzmann relationship, but essentially, if the spacing between energy levels is similar to, or sorry, is much larger, the spacing between energy levels is much larger than kT, where K is the Boltzmann constant, then most of the molecules will be in the ground state, and that's true for vibration in the typical case. However, in vibration, it's much more like, or sorry, in rotation, it's much more likely that you'll have that the kT is such that there are several levels that are occupied, not just the ground level. Some molecules will be in the excited state of the rotation because the energy spacing between those states is relatively small relative to sort of the thermal energy at room temperature, kT. Okay, so let's see. The next thing that we want to talk about is that. Okay, so we have these several J levels, and our selection rule is delta J. So the change in J is plus or minus 1. So that means we can go from J equals 0 to J equals 1. And let's see, okay. And again, if we're talking about the infrared, yeah, we can go from J equals 0 to J equals 1. So there'll be some population in the J equals 0 state. It can be promoted to J equals 1. And also V would be equal to 1, the V quantum number. And we can also have J equals 1, losing a quantum of rotational energy going to J equals 0. So you'd be gaining 1 quantum of vibrational energy and losing 1 quantum of rotational energy. And that would again be for a molecule that's initially in the J equals 1 state. It could be demoted, or it could be switched to J equals 2, something like that. So it can be plus or minus 1. And of course, negative quantum numbers aren't allowed. Negative changes are allowed, right? You can go from 1 to 0, but you can't go from 0 to minus 1. So all of this occurs in the infrared spectrum. And this ends up giving rise to a series of peaks sort of combined with the infrared peak. So we end up with an infrared spectrum that looks a little bit like this. Where you have some sort of central frequency that you can't actually see, but you can infer. And what we get is a series of peaks on either side of that. They're very narrow peaks, so I'm going to draw them with lines, but they might not be actually, if your resolution is high enough, you might actually see that they look like, you know, Gaussians or something. They don't look exactly like lines. So you'll get a series of lines or narrow peaks on either side of a sort of central frequency that you can't see. And one of the peaks corresponds to the delta J equals plus 1 side, and the other set is the delta J equals minus 1 side. And we'll go into why we have these peaks that look like this momentarily, and we'll do that by looking at the energy level diagram, which will help clarify where these different peaks come from. But it turns out that the spacing between these lines, particularly near the middle here, the spacing between the lines is 2b, where I'm using the tilde, the squiggle on top of the b, to indicate that this is b in units of wave numbers. So if the spectrum is in wave numbers, then the spacing between peaks, of course, is going to be in wave numbers. That's not a problem. We can switch to joules. So if we look at the example of HCl, the rho vibrational spectrum, it turns out that the spacing between those peaks is roughly 22 wave numbers. So B is roughly 11 wave numbers. And if we convert to joules, that's going to give us roughly 2.2 times 10 to the minus 22 joules. Okay, so now that we have our B in units of joules, and again, we do that conversion using that conversion between wave numbers and joules that I talked about up here. One wave number is about 1.986 times 10 to the minus 23 joules. So 11 wave numbers would be 11 times that 1.986 times 10 to the minus 23, which gives you roughly 2.2 times 10 to the minus 22 if we just keep 2 sig figs. Okay. And again, we'll explain why the spacing is 2b and not 1b later. First, we want to look at the relationship between this b constant and the bond length. So we know that b is defined as h bar squared over 2I. And so from this we can get I. It's going to be h bar squared over 2b. And see, our b is 2.2 times 10 to the minus 22 joules. So if we use h bar in joule seconds and b in joules, then we're going to get I in mass times distance squared, which is the units for moment of inertia. And of course, we have to be careful to square our h bar. We have to take care of this, be sure and keep this 2 in the denominator. And when we put the numbers in, we get a very small number, something like 2.5, just keeping 2 sig figs to keep things simple. 2.5 times 10 to the minus 47. And that's in units of kilogram meter squared. And you can check with the units there. If you have h bar as joule seconds, square that, divide by B, which is in joules, so you have joules joule seconds, and joule seconds, and joule is kilogram meter squared per second. So you have kilogram meter squared. Okay, I believe I did that right. Feel free to correct me. I just kind of did that off the top of my head. Now let's, I, you may recall, is mu r squared. And for HCl, let's say we're talking about chlorine 35. That's going to give us 35 times 1 plus 35 times the mass of a proton. And I get 1.63 times 10 to the minus 27. So you have to be careful here. This should be in kilograms in order for this to work out. Mass of proton in kilograms. And which is 1.672 times 10 to the minus, I believe, that's my recollection off the top of my head, times 10 to the minus 27 kilograms. And so we get up with a number that's a little bit less than that, right? It's 3536 times the mass of a proton. And we get 1.63 times 10 to the minus 27. And so then, let's see, rearranging this, we get r squared equals I over mu. So we take this big number, 2.5 times, or this tiny number, the large absolute value of the exponent. So that I there, and divided by mu, and that gives us r squared. So r is going to be, this is important, you have to take the square root of I over mu. And when we put the numbers in, we get about 1.25 times 10 to the minus 10 meters. And if you get something like 10 to the minus 20, then that's a good hint that maybe you forgot to take a square root. There's several steps here. And that in terms of angstroms is so angstrom is 10 to the minus 10 meters. So it's 1.25 angstroms. And yeah, that's a fairly typical bond length. The carbon-carbon bond length is about an angstrom or 1.2 angstrom or 1.1 angstrom, something like that. So yeah, typical covalent bonds are roughly on the order of an angstrom, plus or minus 50% or so for the first row or so of molecules. So and the literature value is 1.27 angstroms, and we only kept a couple of significant figures through most of this calculation, and so yeah, so it's not surprising that we get some difference in the third significant figure. And so this is very close to the literature value, which we know from other methods, such as from higher level quantum chemical calculations, things like that. Also from maybe from things like X-ray scattering. And so this is pretty close, right? And so this is a victory for quantum, right? We have finally a way to explain to use spectroscopy to give us information about the basic structure of molecules, in this case a bond length. And of course, for this is for a simple diatomic. It gets more complicated for triatomics and so on, but not overwhelmingly so. That said, I don't want to get too bogged down in the details of that, and so I'll leave that for sort of another course. However, there is a detail that you'll see fairly quickly in this kind of spectroscopy, and that is isotope effects. And there is a vibrational isotope effect, and there's a rotational isotope effect, and they're different. And now previously we looked at the HCl versus DCl and the effect of vibration of the isotope on the vibration. Here, to change things up a little bit, we'll look at chlorine 35 versus chlorine 37, or sometimes the 35 and 37 would be in a superscript before the Cl. We're not going to, yeah, I think it's 35 Cl versus 37 Cl. Those are the two primary isotopes. There are some more rare isotopes, but most chlorine is in one of those two isotopic forms. And remember, different isotopes we think of as being chemically the same, meaning that we expect the same sort of dipole moment for the molecule. We expect the same bond length. However, there are going to be slight differences in the rotational and vibrational spectra. So chemically, they're going to be similar, but there'll be some differences in the spectra. But we can assume that things like bond lengths, spring constant, those kinds of things that are related to the chemical structure are going to be the same or very close to the same for these various isotopes. So this isotope actually is readily observed, especially since chlorine 35 and chlorine 37 are both present in similar numbers. I believe chlorine 35 is slightly outnumbers 37, but you'll end up with, instead of seeing sort of one, you'll see pairs of peaks that are sort of split due to this pairs of so instead of having one set of peaks, you'll have like kind of pairs of peaks very close to each other in the spectrum. So instead of, so I said previously that we had these individual lines, but actually there'll be pairs of lines. Sort of next to each other in these spectra. Pairs of lines that are closely spaced relative to the overall sort of typical spacing between lines. So we'll see that kind of isotopic splitting in our, and I might have got the relative heights wrong there, but I just kind of wanted to show, roughly speaking, they're going to be fairly close to each other, these isotopically split lines in the rotational spectrum, particularly for this chlorine 35 versus chlorine 37 case. Now, so you may recall for vibration, our frequency is proportional to square root of k over mu. And we think the principal effect of the isotope is that it affects mu, it affects the reduced mass. And so we end up with nu2 over nu1 is equal to the square root, since it's proportional to the square root in the denominator, then that's going to give you an expression that looks like this, where we have nu2 over nu1 is equal to the square root of mu1 over mu2. And there's a lot of potential for confusion about which is 1 and which is 2 in a given system. And so the thing to keep in mind is that heavier molecules are going to have lower vibrational frequencies. So you expect the frequency of DCl to be lower than HCl. Now for rotation, in contrast, see, we know that B is h bar squared over 2I, and I is mu r squared. Again, we decided the principal effect of isotope is it changes the mass. It changes the reduced mass here, mu, and it doesn't change r. So, so it's proportional to 1 over mu, not square root of mu, 1 over mu. So therefore, for the rotation, B2 over B1 is equal, according to our proportional reasoning here, is going to be equal to mu1 over mu2. So for so let's see. So for going back to vibration for a second, the DCl versus HCl. For HCl, we have that nu is about 2900 wave numbers. And for DCl, nu would be equal to roughly, since DCl, the reduced mass is roughly double the reduced mass of HCl. And so we get that it's roughly 2900 over square root of 2, because there's the square root. And so we end up, we expect something that's going to be roughly we'd be looking for a peak at roughly 2050 wave numbers. So if we have some sample that we think has some DCl in it, and we stick it in a FTIR, we would expect to see a series of peaks centered at roughly 250 wave numbers due to the vibration. Now, at the same time, we're going to have chlorine-35 and chlorine-37. So let's look at the effect there. So our mu for chlorine-35 is going to be 1 times 35 over 1 plus 35 is, and again here we're just using the sort of integer masses, and so that's going to give us roughly 36 times the mass of a proton. And for chlorine-37 in HCl, we're going to have, again, we still have H. We're not looking at deuterium here yet. Well, we already treated deuterium for the vibrational case. So here we're looking at the rotational case, and see, we're going to get 37 over 38. And times the mass of a proton. And so mu1 over, or mu, say for 35, or mu for HCl 37 is roughly 35, 36 times 38 over 37. And that's roughly, it's going to be just a very slight change. We'll keep a few sig figs, just enough to see the change. If we just keep 2 sig figs, it's just going to be 0.99, which isn't enough. So we'll add a couple more sig figs, 0.9985. Okay, that's enough that we can see that, yeah, this is a number that's a little bit less than 1. So we expect that B would be differing by roughly about 0.15%. And we expect that it's going to be lower for chlorine 37 because it's heavier. Okay, and we can go through a similar calculation, and the vibrational frequency is going to change by a little bit less. Because there's a square root involved, and it's roughly 0.075%. And since in an FTIR you have typically about a 0.1 wave number resolution, and these spacings between peaks are on the order of 10, 20 wave numbers, so you can actually resolve the different isotopic peaks in chlorine. In HCl. Okay, so that's the rotational isotope effect. Now let's go back to an energy level diagram and try to understand the shapes of these spectra a little bit more. If we look at the energy level diagram and we apply the selection rules, then the combination of those, and if we know something about occupancy, then this is going to tell us what peaks are present. And it's going to tell us about how the spacing between peaks is related to the rotation constant. And once we know the rotation constant, then we can get information about the bond lengths. Okay, so there's a couple of ways of looking at this. One way we can look at this is we can start by making a table, and we can also look at the energy level diagram So if we look at a table, our allowed values of J, we're going to keep a few values of J. I said at least the first few levels are occupied. So we're going to have J equals 0, 1, 2, 3, 4. And then we're going to look at B times J plus 1. That's EJ. And then there's going to be, for each level, or for most levels, not every one, there is going to be a delta E So there's going to be a difference in a given energy level J and its next highest level, the J plus 1 level. And for the J equals 1 and higher levels, there's going to be a delta E for J going to J minus 1 for that transition. And we're going to give these energies in terms of B. So for J equals 0, we get B times J plus 1. We get 0. For J equals 1, we get an energy level of 2B. For J equals 2, we have B times 2 plus 1. So that's going to be 6B. And for J equals 3, we're going to get 12B. And then for the next one, we get, for J equals 4, we get 20B. Okay, so then the next column is going to be fairly simple. We'll look at the difference between, say, J equals 0 and J equals 1. Well, the difference there is going to be 2B. And then the difference between J equals 1 and J equals 2, that's going to be 4B. And then the difference between the J equals 2 state and the J equals 3 state is going to be, and that's going to be 12B minus 6B, so that's going to be 6B, and 8B, and that's enough. Okay, then, so those are the differences in energy when we go from J to J plus 1. So that's going to be the spacing, or that's going to show up in our spectrum as we see. Because in our spectroscopy, one of the rules of spectroscopy, we're not measuring the energy of a system, we're measuring the difference between two energy levels. And so it's these differences as a function of quantum number, those are what's going to show up in the spectrum. It would be simpler, I suppose, if spectroscopy just gave us the energy, right? But that's not the way it works. There are energy levels, and those energy levels plus the selection rules give you a series of lines, and so you get this perhaps somewhat complicated looking spectrum, but it also has, the flip side is it has a lot of energy, or sorry, has a lot of information. Okay, so let's look for, now for J equals 0, well, you can't go from J equals 0 to J equals minus 1, so we don't, that's just kind of a, we'll pass on that one. For this one, we get minus 2B, right, that the difference between J equals 1 and J equals 0 is going to be minus 2B. For the next one, we get minus 4B and minus 6B and minus 8B. Okay, so that's one way of looking at the energy levels of the system. Now let's look at an energy level diagram. our lowest energy level is, let's see, let's put J on the left and EJ on the right. So we have J equals 0, J equals 1. J equals 2 will be here. And J equals 3 will be there, roughly. So our energy is going to be 0, 2B, 6B, and 12B. And the energy associated with these transitions, right, between, say, J equals 0 and J equals 1, that's going to be 2B. That's going to be 4B. That's going to be 6B. So if each of these is occupied, then we would expect to see, and of course we're dealing with the transition from a central frequency, then we would expect to see peaks at 2B and 4B and 6B, and at minus 2B and minus 4B and minus 6B from our central frequency. So we expect that our spectrum is going to look a little bit like this, where we have our central frequency, that's dictated by the vibration, and then so that's from the v equals 0 to the v equals 1 state, and then on top of that we have these rotational peaks. So the spacing away from the central peak is going to be 4b, and then thereafter the spacing between the peaks, ignoring the isotope effects. No, I didn't get those spacings quite right. And then the spacings between these various peaks are going to be 2b. And so by looking at this spectrum, and again looking at this sort of table or this energy level diagram, we can see these relationships between sort of where these transitions are, indicated by the double arrows in the energy level diagram. Each of those is going to give rise to a peak shift from the central frequency. And you're going to have a series of these on either side of the central frequency. And most of the spacing for the delta J equals plus versus delta J equals minus 1, that's going to give you 4b in the middle there, but then afterwards, all the spacings are going to be 2b. And so we can interpret our vibrational spectrum to give us information about this rotational constant B, and then from that rotational constant B, we can get information about the bond length in the molecule, and also maybe some information about things like isotope effects. And you'll have a chance to explore these concepts in some more detail in the associated assigned problems, which will be given. But that wraps up our discussion of the rotational spectroscopy of diatomics and how it relates to the rigid rotor model of quantum mechanics.